Okay, so thank you, Ursula. Thanks to all the organizers. Thanks to all of you. So what I'm talking about today, this is all going to be joint work with these four lovely folks behind me. Apparently, we forgot to send Alachar the memo for like the group photo shot of, tilt the head, smile, make sure it reaches the eyes, don't let Tyra down. But this is work in progress. Everything I'm saying today is done. There's just some extensions that I'll talk about a little bit at the end that are hard and have been slowing things down. So things are not out yet, but hopefully soon. And so where I'm going to start in terms of motivation is with a 2016 paper of Barry Mazur and Carl Rubin. It's kind of a survey overview paper where they're setting a program for diophanting stability, as they call it. And really the main overview of what they're thinking about is to what extent does knowing the algebraic data of a curve tell you about the geometric data, right? And so geometric, isomorphism class over C might be what we want to think about. On the algebraic side, I'm going to be thinking about algebraic points, and specifically, we'll understand the algebraic points via the number field side of things. So I'm going to let gay F of gay C, I've got a lot of gay letters, I came prepared, is going to be just every number field over which our curve attains a new point. So every finite extension of Q where there's a point on the curve that wasn't there in any prior extension. And then as an example of somewhere where this really does determine the curve, if you can get every number field, if there's always new points, then your curve was P1 or isomorphic to P1 to begin with. And then we can think about how well does this generalize. So a question that they sort of pose in the paper, certainly not a conjecture, just a thing to think about, is if we know that two curves generate the exact same number fields, are they necessarily isomorphic over C? And if not, maybe what other barriers would live there? This is not a question that I'm going to be thinking about, but we're just going to take this and flip it the other way around. So conversely, we could say, from the arithmetic statistics perspective, here's a collection of number fields is a thing we get excited about. And so let's say if we fix a curve C, what then can we say about this collection of number fields? And specifically to do that, we're going to add in one more thing on our set of number fields where we're going to add an ordering by the size of the absolute discriminant. And by doing that, this is now a finite set. And so we can ask about how big it is. We can ask how that count behaves asymptotically, right? And before getting to that, I want to just step back and review some things on the arithmetic statistics side, and specifically how this behaves if we don't have a plane curve. If we just want to look at number fields of bounded discriminant, how does that work? We're also going to be fixing the degree of the number fields throughout. So if we want to ask how many number fields of degree n are there with discriminant bounded by x, the main takeaway, if you haven't seen or thought about this before, is that this is really, really hard and we can't say that much. So to get us in the mood for that, there's a standard conjecture that we don't even know who to attribute it to. It's always this might have been Yuri Linnik, which is, it might have been a lot of things. But the expectation is that this is always linear. No matter what your degree is, the growth, this counting function, is going to be linear in x asymptotically. And again, in general, we know very little, but in small degrees, we do know that this is true. So for n equals 2, this just follows some classical results of quadratic forms. You could attribute this to Gauss if you wanted to. N equals 3, 1950s, 60s, Davenport and Heilbronn showed that using class field theory, essentially. And then n equals 4 and 5, Manjul Bhargava, as a consequence of his dissertation work, higher reciprocity laws, established 4 and 5. This is like a big contribution to why they gave him a Fields Medal. Even in 4 and 5, this is a very, very big problem. And beyond that, there's a lot of work in 6. It's conceivable that we'll know degree 6 sometime soon. Beyond 6, even like 7 and above, we're very, very far away from really being able to say too much. And so if we can't get exact asymptotics, what we can do instead is we can say, well, can we get lower bounds? Can we get upper bounds? Today, I'm just going to be looking at lower bounds. And again, in just counting number field setting, just introducing, I'm going to let capital N, a straight N, be that counting function we've been talking about. And the really big breakthrough here from 2006 was an annals paper of Jordan Ellenberg and Akshay Venkatesh, where they show that this counting function is asymptotically larger than, or bounded below by x to the 1/2 plus a little bit. There have been improvements to this since then, but only in the error term. So now we can say 1/2 plus essentially 1 over n, but there's been no improvement in the 1/2 in the 20-ish years since here. And so I want to just briefly talk about some of the methods here, because these are going to be the methods that we want to adapt to the problem of adding in this plane curve. And so very, very broadly, their approach to this is like a nice, just the most naive thing possible of, we're just going to count as many number fields as we can. However many we found, there are at least that many. That's the lower bound, right? So the way we're going to get to number fields is through defining polynomials. So we're going to start with what I'm going to call a universal polynomial of degree n. I'm just putting universal in quotation marks to mean that I don't mean anything particularly technical in using universal here. Just so that we can start with a degree n polynomial where my coefficients I'm thinking of as parameters in some function field. So I could get any degree n polynomial over Q out by just specializing the coefficients, right? And what's nice about working over this big function field to start with is that then we can use Hilbert irreducibility theorem, which is going to say that 100% of the choices of particular coefficients you take from here are going to yield an irreducible polynomial. And then in the standard way, you know, Q bracket x modulo that polynomial, we're going to get a number field K. 100% here is in an asymptotic sense, where the ordering is a universal bound on each of the coefficients. So assume all coefficients in absolute value are less than some x, let x grow, and then the proportion of these polynomials which were irreducible goes to 100%, right? So then a big part of the work here is to go from that universal bound on like the height of the polynomial, we'll call it, turn that into a bound on the discriminant of your number field K that you get out, so that we can turn this into, you know, knowing that we have a field we want. And then there's also a big thing that's still left, which is that multiple polynomials can give you the same number field, right? X squared plus 1 is going to give me Q adjoined I. The minimal polynomial of 1 plus I is also going to give me Q adjoined I. And so then they do a lot of geometry of numbers to kind of figure out how many times could we have gotten the same number field from different polynomials. Divide that out, you get this count, right? So that's very, very simplified overview of their approach that is going to be what we want to do in just moving over to this plane curve situation. Okay, so now back to the plane curves, right? We're just going to take the counting function in general and then just say we only want to count those number fields where we get new points on our fixed plane curve C. And so if we want to adapt Ellenberg and Venkatesh's overall approach, we need to somehow only look at polynomials that are going to correspond to a new point on C. And then this is going to be where my first restriction on the curve, so this is where the plane curve assumption is going to be really important to us. To get to a polynomial, we're going to want to start with a polynomial model for the curve. So I'm going to let f just be my polynomial model for the curve we're starting out with. And then the idea is going to be that to get to a polynomial where there's a point, an algebraic point on this curve, we can intersect this curve with some parametric curve. So introduce some new curve P of t, parameterized by t. Assuming everything here is algebraic, these are going to intersect at an algebraic point. And when we take the intersection, we'll get a rational function in t, but we can clear denominators to get a polynomial in t. And that polynomial is going to define a number field where we get a new point on the curve. That new point is just take a root alpha of this polynomial, put it in at P of alpha. And that's the intersection point. We know it's algebraic. And so this is going to give us polynomials where we know that we're getting new number fields. There are going to be restrictions. So we're going to fix the degrees of A, B, C, and D in a bit. But then we're going to let the coefficients vary kind of in the same way that for Ellenberg, Venkatesh, they're like, so this polynomial little f we're going to want to think about as being over some really messy function field, and then look at specializations to get as many. So yeah, we'll fix the degrees in order to fix the degree n. But yeah. Okay. And so on that with degrees, I guess one thing that I'll just say here, because we're fixing the degree of the number fields, there are going to be some curves that don't have any points of degree 3, or any points of any odd degree more generally. And so if we wanted to fully generally give a lower bound that will work for any curve at any degree n, we're never going to do better than 0, because there will be some choices of n for a curve where there are no n degree points on the curve. And so the first thing that we're going to want to think about is which degree should we be looking at for our fixed curve C. And so we've got a new queer D coming in. This is just going to be the set of degrees we should look at. So the set of degrees where there are number fields of degree n generated by our curve, so there are points of degree n on the curve, right? And thinking about this coming from like intersecting with this other curve, so this is just the notation from the last slide. And now I'm fixing the degrees of the various polynomials defining like this parametric curve P. And what'll happen is that if we just look, if we want to know what the degree of f is after we take the intersection, we can just think about what's the degree, the maximal degree among the monomials. And that's going to be the degree of the overall curve, assuming you don't have like cancellation in the leading coefficient, which 100% of the time you won't. And so we look at a fixed monomial x to the I, y to the j. When we intersect and clear denominators, we get this polynomial over here, which has degree given by this. So this is the degree of each monomial after we take this intersection. The second half of the degree here, this is all fixed, right? We're fixing our model, we're fixing little a, b, c, d. So really that if we want to know what the degree of the overall polynomial we get is, we just need to look at this part. A minus b times I plus c minus d times j, figure out which monomial x to the I, y to the j is going to maximize this. It's just a linear function, right? And so it's going to be maximized at the most like extremal x to the I, like ij's, right? And so to make that a little bit more precise, if we want to know which degrees we should look at, we can do that by just looking at the convex hull of the tuples ij such that x to the I, y to the j shows up in our model. So with our model again given by this f of x, y here, we can take the convex hull of all of the tuples ij such that the coefficient is non-zero, it's actually contributing to the polynomial. And then at each vertex of that convex hull, I'm going to take the greatest common divisor of the coordinates of that along with the x degree of f and the y degree of f. And that's just because coming from this term here, if I want to know what this degree is, I can choose this basically to be any sufficiently large multiple of that GCD, just doing like elementary number theory. Okay, and so what we're able to say is that for every sufficiently large multiple of m, we're going to be able to generate infinitely many number fields from our curve C. So these are going to be the degrees that we want to look at, is just this kind of very combinatorial way, just look at the convex hull, take all the vertices, compute this GCD, any sufficiently large multiple of those we know we can get. So to go through an example, just to make this a little bit more concrete, we have gauge, let's stick with gauge, being a hyperelliptic curve with model y squared equals some degree d irreducible polynomial in x. Then the convex hull, so when we plot the vertices, we have a 0, 2 from y squared, and then the polynomial in x is just giving us a lot of like I zeros. So our convex hull is just going to be this triangle, and the x degree is d, the y degree is 2 of our model, right? And then we'll look at the 3 vertices, compute this GCD. So for 0, 2, that GCD we get is going to be 2 if the degree d is even, 1 if it's odd. And the same thing is going to happen at the other vertices. So if we look at 0, 0, this is corresponding to the constant term in the equation. That's going to give us all even degrees if d is even, all degrees if d is odd, and same thing for this final vertex over here. Right? So to summarize, what the theorem is telling us in this case is that H is going to be generating infinitely many number fields of all sufficiently large, even degrees if d is even, and all degrees if d is odd, right? And part of why I wanted to use this as the particular example is because we know a lot about hyperelliptic curves, and so we know that this restriction is actually necessary by a result of Bhargava, Gross, and Wong, which says that a positive proportion of hyperelliptic curves with D even, of locally soluble hyperelliptic curves with D even, are going to generate 0 number fields of odd degree. So at least in the case of hyperelliptic curves, we know that we're not missing degrees in generality, that there aren't like more degrees that we should be looking at. This restriction that we're getting here is necessary, at least in this case. Okay, and something that I didn't mention, but in proving that theorem, this is also going to tell us how we should choose little a, little b, little c, little d to get a fixed degree n out. So if you give me some n that is kind of valid coming from that previous result, then I can also give you how I should be choosing the degrees of a, b, c, and d in order to get that degree out. Yeah, I'm going to just go ahead and now this polynomial we get after we take this intersection, I'm just going to call that capital F of t to simplify the notation for the next little bit here. And so in the same way that Ellenberg and Venkatesh have their universal polynomial of degree n, I can now choose a sort of universal polynomial of each of these 4 degrees, a, b, c, and d. And now this polynomial capital F, we have like a sort of universal polynomial of degree n for whatever our fixed n is, which is now a little bit more complicated than what they had, right? Because our coefficients are going to be like polynomials in the parameters. And so a lot of the work then goes into, this is not like a completely random polynomial of degree n, but it's close enough to being random that it's still going to be irreducible 100% of the time, that we can still translate between bounds on the coefficients of this thing into bounds on the discriminant. And so, there's a lot going into this final sentence here, but basically this is going to give us, again, a sort of random degree n polynomial that we can specialize to get a different number field. And it's random enough that we're not like influencing the fact that this should behave nicely most of the time. Okay, and so then going through a lot of the machinery that they develop, we can get to an asymptotic lower bound now for the function that we want. There's some technical reasons that we have to restrict to genus at least 2. You certainly want positive genus just for this to be a slightly more interesting question than just for a P1. But we're able to say that the number of number fields of degree n generated by the curve C, discriminant bounded by x, eventually grows faster than x to the c sub n, where this c sub n is a completely explicit exponent that goes to this 1 over the minimum of the x degree and the y degree squared as n goes to infinity. This having the n and the c in the subscript on the greater than just means the implied constant can depend on choice of degree, choice of curve. Really choice of model, I should say, not choice of curve. And I'll just note that this recovers some previous results of Robert Lemke-Oliver and Frank Thorne, Chris Keyes, and then Leah Benesch and Chris Keyes in the setting of elliptic, hyperelliptic, superelliptic curves. I have an asterisk on elliptic because obviously a theorem that's only true for genus greater than or equal to 2, saying that that recovers facts about elliptic curves is a little bit obviously false. There's like one technical part where we can't do genus 1, and if we could work around that, then what Robert and Frank have for elliptic curves, if you just assume that we could have genus 1, their result would fall out. It's just to prove things in complete generality, we end up needing to treat that as a slightly separate case. Okay, so I'll just finish by just summarizing with like one explicit example and see what we can have. So here's a curve. This curve isn't that particularly interesting. It just has enough monomials for the convex whole to be more than a triangle, right? This is what the curve, at least the real part of the curve looks like. So again, we start by just plotting all of the tuples ij, such that x to the I, y to the j is part of my defining equation. And in this case, and what will often happen is one vertex is going to be good enough. So I look at x cubed, y squared, 3 and 2 are relatively prime. So when I compute that relevant GCD, we get 1. And so this, then we know that we can look at any degree that's a sufficiently large multiple of 1. And in this case, sufficiently large just means at least 5. So there's a lot of things that go into sufficiently large, but generally what you should take sufficiently large, what I expect it to be is about the degree of the curve, of the defining like polynomial. Right, and so we know that for any such degree, this curve is going to generate a number of fields of that degree that's going to grow eventually faster than x to the 1 over 16. Right. Okay, and I'll just finish with a few further directions. So there's probably two obvious things. We're talking about lower bounds. What about upper bounds? The methods for upper bounds on number fields is very, very different. You roughly think about like the ring of integers as a lattice, and then you're trying to choose an optimal basis of that lattice. So there might be ways to get that to be kind of relate to the curve if you look at the Jacobian of the curve. But I think you'd have to have some pretty new ideas to be able to say anything about upper bounds in this case with a plane curve. As far as generalizing plane curve, a lot of what we do should work for hypersurfaces, at least. Like if you have a polynomial, at the level that I've talked about it here, everything works. In the details that I'm not talking about, there's a lot of work you would have to do. And then something that's maybe not as obvious of a question, but that is the thing that's keeping us from finishing this paper is we really want to only count those number fields which have Galois group Sn, in the sense that like their Galois closure has Galois group Sn. Because if we can do that, then we can construct like towers of number fields just using some results in arithmetic geometry where the Jacobian of the curve grows in rank. And we like to be able to do that, and 100% of polynomials have Galois group Sn, so the count should be the exact same. It's just hard given a big, messy polynomial to check that it actually has Galois group Sn. I will go ahead and end things there.